people of grade 10 math. Boy, do we ever have something special for you.
Zoo!
Special quadratic expressions. So, we are going to kick things off by doing a little bit of expanding and simplifying. As you notice, all the things that we're going to expand and simplify here are actually the same thing, except for the sign in the middle is different. Right? So we have 3x minus y here and 3x plus y there. We call these pairs of binomials conjugates. So with the same term, but with a different sign in the middle. Alrighty. So we're going to expand and simplify. So essentially, we're going to do that double distribution. When I distribute my first terms, I get x squared. My outsides, I get minus 2x. My insides, I get plus 2x. And my left's, I get minus 4. Now, of course, I'm going to collect my like terms, and those are my terms with the x variable there. And I end up with x squared minus 4. Whoa, we don't have any x term at this point. We have 0 as my coefficient for that bx term. That's kind of cool. Let's try another, shall we?
Okay.
What about this one? Well, same. When I multiply my firsts, I get that x squared. My outsides, I get that positive 5x. My insides, I get my negative 5x. And my lasts, I get negative 25. Well, again, going to collect my like terms, which are my terms with the x. I end up with x squared minus 25. And again, that middle bx term disappears because my coefficient there would be 0x. And I'm not going to write down 0x. Alrighty. What about this next one?
Oh, let me tell you. Well, let me tell you in purple. That's a certified thick pen. Oh, that's normal. Okay. So as I was saying, I'm going to tell you about this. I'm going to FOIL this out. I'll take my 2x times 2x to give me 4x squared. Here's 2x times negative 3. So that's negative 6x. 3 times 2x to give us plus 6x. And 3 times negative 3 for good old negative 9. And of course, we're going to simplify that. Whoa! Negative 6 and positive 6. That's a whole lot of nothing. So we've got 4x squared minus 9. And certainly you've already tried to pause and do the next one on your own. But here I go for it. I'll say that this product is equal to 9x squared plus 3xy minus 3xy minus y squared. And, gosh, color me surprised because these middle terms cancel. And I'm left with just 9x squared minus y squared. What on earth is going on?
You know what? Let's chat about it. These guys are real special. Special how? Well, they all kind of have the same pattern going on. So a couple of things that we might notice is that middle term in our basic ax squared plus bx plus c type of trinomial, well, our bx term always cancels out to get or to give us 0x, right? But of course we don't write that 0x. Okay? So that's one thing we might notice. Another thing that we might notice is that both the first and last terms are perfect squares. What? Right, so if I'm looking at this guy here, my x squared's a perfect square. because I get x times x. And this 4 is a perfect squared because I have 2 times 2. Same, when I look at this next question, 4x squared is a perfect squared because it's 2x times 2x. In the same way that 9 is a perfect squared where I get 3 times 3. And I could go ahead and look at them for all of these. So, x squared is x times x, 25 is 5 times 5. 9x squared is 3x times 3x, and y squared is y times y. Whoa! So my first and last terms always end up being perfect squares. And the last thing I might notice is that my first term is always positive, and my last term is always negative. So what I have going on here is that between each of these examples, I have a difference. I have a subtraction statement. So if I have something where I have 2 squares and I'm subtracting them, I end up getting something called the difference of squares. And that's going to be a special kind of factoring method that we're going to be able to do. So when we do that, that's what the result is called. It's called a difference of squares type of factoring. The key point is that anything that we start with, if we wanted to go ahead and factor these backwards, and we were given this type of statement to factor, it can be factored in the following way, where we have a plus b, where a is the square root of my first term, b is the square root of my second, and then I have its conjugate, which is a minus b. So notice that in my difference of squares, when I'm factoring that, my first term is always going to be the square root of my first perfect square, and my second term is always going to be the square root of my second perfect square. Lastly, I want green. My signs are going to be opposite. So I'm going to have one binomial with a plus sign with the addition, and one binomial with the minus sign with that subtraction. Alrighty. Do you think we can give this a try?
I do. So let's see how to factor these examples. If you feel like you're already ready to give it a try, for sure, give it a go. Give it a stab. Give it a shot. Give it a whirl. Here I'm going to go do it in blue. We can recognize this as a difference of squares because this first term is a square of x. The second term, as I switch from squares to arrows, is the square of 3, and there's subtraction in the middle. So we've got subtraction between 2 perfect squares, a difference of squares. That means I can factor it by using that x and that 3. They'll look kind of same, but the difference is that one will use a plus, one will use minus. We'll do the same on the next example. 25x squared minus 1. Where did 25x squared come from? Well, it is the square of 5x. Where did 1 come from? That is a perfect square as well. That's the square of 1. So, when we factor this, recognizing that it's a difference of squares, we can say that both of these will involve 5x and 1, where 1 has a plus and 1 has a minus.
Alright, and if you haven't hit pause yet, this would be the perfect time to do so, and try this next couple of examples on your own. Alright, so when I see this, notice that one of the key differences between the factoring that we've done before and the factoring that we've done now with the difference of squares is that now with the difference of squares we only have 2 terms. So that's a big indicator of we should be looking for that difference of squares if it's possible, right? And it won't always be possible unless we have those 3 conditions met. First condition, first term is a perfect square. Second condition, last term's a perfect squared. Third condition, there's a difference, right? It's called difference of squares because we're subtracting perfect squares. Now, what is the square root of 16x squared? Well, that's 4x, right? Because 4x times 4x gives me 16x squared. What's the square root of 49? Well, that's 7, because 7 times 7 gives me 49. So I know that both of my binomials will include 4x and 7. And they will be conjugates of each other. So the first one will have a plus sign. The second one will have a minus sign. They have opposite sides. Keep in mind that it actually doesn't matter which one has the plus and which one has the minus, as long as they each have something different. So I could have very well had said minus and plus and still get the same response. All right, this last one here. Whoa, we've got more variables than just x. That's okay. We're tough. The square root of 36x to the 4 is going to be 6x squared. And the square root of 121y to the 6 is just 11y cubed. And of course, there is that difference there. So I can see that it is a difference of squares. So I know both of my binomials will include the 6x squared and the 11y cubed. 6x squared, 11y cubed. One will have a plus, one will have a minus. They will be conjugates of each other. Does it matter which is which? No. I'm going to put the minus first. Oops, so sorry. And the plus second, just to spice things up.
You're saying that's the same?
That's the same.
Well, that's neat. Good to know.
Wow, that was so much fun. I wonder if there's other types of special factoring that we could look at.
I'm so glad you asked, because actually, if you just flip the page, there is another one.
Wow! Another one.
I have no response. We're going to also look at a perfect square trinomial. What makes something a perfect square? Well, you get a perfect square by multiplying something by itself. Just like 2 times 2 is 4. 4 is a perfect square. Or 5 times 5 is 25. 25 is a perfect square. It's the result of taking something and multiplying it by itself. Where 2 times 2 is 2 squared. 5 times 5 is 5 squared. So we can see perfect square trinomials if we take certain binomials and square them. What's key to note here is what that squaring means. We can't just take that exponent and say that we're distributing it.
What? Why not?
Because it's bad. But if you want to see that in action, try something out. Try something like 1 plus 2 squared and see what happens. Now remember, there's an order of operations that this addition has to happen first before we square, which means we're really looking at 3 squared, which is 9. But if you try and distribute that, if you say, oh, I can just take this exponent of 2 and go blip, blip, you'll get 1 squared plus 2 squared, which is 1 plus 4, and that's 5. These are not the same. So the order does matter. We cannot just distribute an exponent like that. It doesn't work. But we can look at what it means to square something. And when we square something, as stated a moment ago, it means you multiply it by itself. So to square x plus 3 is to say that we're going to take x plus 3 and multiply it by itself. This is a very key step that's crucial that you understand. Once we have it in that form, though, we can use FOIL to go ahead and actually distribute and open up these brackets. So then we can say that we've got x squared plus 3x from the outside, and then inside is a 3x again, and last terms gives us 9. And to collect them all, we've got x squared plus 6x plus 9. Feel free to try the others. I'm moving along, zippity-doo-dah. What does it mean to take x plus 1 and square it? Key step is to write it as x plus 1 times x plus 1. Multiplying x plus 1 by itself, and then we can use some aluminum foil. So our first term gives us x squared. Outside is x. Inside, that's also x. The same thing. And then last term's product is 1. Finally, collecting like terms, there's where we at.
All right, and we can try the next two examples. And if you haven't paused already, please pause now to give it a go. But otherwise, we are going to take the square of 2x minus 9. And again, if we're squaring that binomial, that means we have to take the whole bracket and times it by itself. And from there, we can go ahead and distribute, do that double distribution, and get 4x squared minus 18x minus 18x plus 81. And I can collect my like terms here. Let me go 4x squared minus 36x plus 81. Isn't it nifty that these guys are identical?
What a strange coincidence.
Whoa, it happened here too?
Wait, what?
Hey. Okay. You know what? It's happened a couple times. Let's see if it happens again.
Probably not.
Nah, it's probably just a fluke that happened 3 times. All right. So we have this guy here. We are squaring it, which means we're multiplying it by itself. And then we need to go ahead and distribute. So we end up with 25x squared. Let's see if it works. Minus 20x. Minus 20x. Plus 16. And we're going to collect those like identical terms. And get 25x squared minus 40x plus 16. Whoa. Cool things are going on.
So what we're going to look at is where each of those terms comes from. So when we squared x plus 3, could we have predicted that we'd get an x squared and a 9 and a 6x? When we're squaring x plus 1, could we have predicted this particular trinomial? When we squared 2x minus 9, where did the 4x squared come from? Where did 81 come from? Where did negative 36x come from? And when we squared 5x minus 4, how did we get each of these pieces of the trinomial? That first term, here being x squared, here being 4x squared, where does that come from? Well, that happens to be from our first terms product, which being x times x is actually just this first thing squared because it's being multiplied by itself. If I had a pen, I could probably write that down. So the first term of the trinomial comes from the square of the first term of the binomial. Where does that last term come from? Why is this one 9? Why is this one 81? Why is this one 1? Why is that one 16? Well, that's because of our last term's product here, 3 times 3. And we're multiplying 3 times 3 because it's this binomial times itself. So it's the second term of the binomial being squared. And then there's this really special middle term. Because if we're talking about a perfect square trinomial, it's not enough that the first and last terms are perfect squares. There's something very special about that middle term. And let's look at where it comes from. Here we had 6x. Where did 6x come from? Well, it came from 3x being there twice. Why was 3x there twice? Well, when we took the OI of this FOIL process, we had x plus 3, or x times plus 3, and plus 3 times x. We had that product twice because that binomial is getting multiplied by itself. The O and the I were the same thing. They were both 3x. Similarly over, let's pick this one just for funsies. This outside product, this inside product, they were the same thing. They were both 18x. It happened twice to give us this negative 36. Why is this one negative 40? It's because negative 20x happened twice. And negative 20x happened twice because of the matching OI. Where we get that from is the product of the terms of the binomial. The 5x times negative 4 is what gave us each of these negative 20s. We had two of them because we're multiplying that binomial by itself. That is the key that unlocks this perfect square business. So, where does this perfect square, or this middle term, come from? It is 2 times the product of each of the terms of the binomial. So if you want to quickly square something, you can use this formula here. I have the ability to highlight it, don't mean to brag. Boom. Where we're saying it's the first thing squared, it's the last thing squared, and in the middle is 2 times their product. And if this has a subtraction in the middle, well, the first and last remain the same, but now our b value is going to be negative. That's the sole difference between a plus b squared and a minus b squared. Anything you would add to that?
No, I think you did a good job.
Oh, thank you.
And I think we continue to do a good job by kind of looking at that backwards. So right now, what we've done is we've looked at expanding and simplifying what's already been factored, right? We factored and noticed that it's a perfect square trinomial. However, in this unit, we're starting with that perfect square trinomial and wanting to factor it rather than going in reverse that we just did. So what we can do is we can use that pattern we just discovered, but only if we're able to spot that perfect square trinomial at the beginning. So if we're wanting to spot that perfect square trinomial, we're going to see, well, is that first term a perfect square? Is that first term a perfect square? Oh, I didn't want to draw it. I wanted to highlight it. Boop, 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 boop. Okay, now let's try it again. Is my first term, missed T. Okay, is my first term a perfect squared? Okay, that's good. Is my last term a perfect squared? Okay, that's good. Now, if I were to look at each of those terms and distinguish what the square root of each of those would be, right? This would be A. The square root of this would be B. And I multiplied those two things together. So A times B is AB. And I did that twice, right? Because if I multiply that same binomial by itself, I'm going to get 2 times that product. So if I end up with 2 times the square root of my first term times the square root of my last term, I should be able to acknowledge that that's a perfect square trinomial. And really, spotting that is the hardest part. But once you've spotted it, the factoring becomes really easy. So let's take a look. At this first question here, I'm going to look, is it a perfect square trinomial? Right? I am starting off by saying, hey, is this first term a perfect square? Well, is it? Yeah. this is the same as x times x. Well, what about my last term? Yeah, that's the same as 2 times 2. Well, what about my middle term? Right? Remember that my middle term has to be 2 times the product of my A term, which is x, and my B term, which is 2. So is my middle term, in fact, 2 times... Ooh, I did not want that highlighter. 2 times x times 2? Well, yeah, because 2 times x times 2 is really just 4x. So I can acknowledge that this is, in fact, a perfect square trinomial because it follows that same pattern, that same criteria that we noticed before. So in factoring this, we could actually get rid of all this information here because we just wanted to use it to acknowledge that it's a perfect square trinomial. To do that, I know I'm going to end up with something in my bracket to the power of 2. Something in my bracket squared. Okay. Well, what goes in my bracket? Well, I'm going to move this down. My square root of my first term and the square root of my last term go in there. So I'm going to have x and 2. Now the sign is what we're going to look at. And in this case, my middle b term is positive. So what goes in my binomial is going to be a plus sign. Okay. All right, let's try another example as well. This guy here, we are going to look, is this one in fact a perfect square trinomial? So we're going to check. Is the first term a perfect square? Yes, it is. Its square root is x, right? X times x gives me x squared. Is my last term a perfect squared? Yes, it is. And its square root is 2 because 2 times 2 gives me positive 4. Now, is my middle term, follow that same pattern. Remember, my middle term had to be 2 times a times b, right? And in this case, my a value is the square root of my first term, 2 times x. And my b term is the square root of my last term. So I'm going to get 2 times x times 2, and I get 4x. And yes, in fact, it is 4x. All right. Now, we want to try and factor that. As we're factoring it, because we've identified it as a perfect square trinomial, we're going to get a binomial squared as my final factoring piece. What goes in that bracket? Well, it's the square root of my first term, x, the square root of my last term, 2, and the sign of my middle term, that negative. So I'm going to end up with x minus 2 squared.
Here's another one. I noticed some things that make me think maybe it's a perfect square trinomial, because you can see that my first and last terms are perfect squares. So proceeding with that, I can say, well, this came from an x, this would have come from a 6, and 2 times their product, 6 times x is 6x, 2 times that is certainly 12, but yoinks, that's a negative 12. So I'll note that I will have an x and a 6 in here, but there will be subtraction. So again, the square of the first term gives me the x squared. The square of the second term gives me the 36. And 2 times their product, because their product is negative 6x, and that times 2 is equal to our middle term right up there. So we solid, we good to go. And there's this beast. Oh my goodness. Might not even recognize this as a perfect square right away. And if you don't, that is okay. Like, we can always use our other factoring methods. And then if you happen to notice that it factors into two things that are the same, all hunky-dory, we can move on. But here we go. I see that this is a perfect square. I see that it comes from squaring 3x. I see that this comes from squaring 5, so I'm hoping that this 30 works out. Because the product of 3x and 5 is 15x. 2 times that product is 30x. So, wazoo! This does work as a perfect square trinomial. And I can say that will involve a 3x and a 5. This is positive, so this is positive, and I am squaring it.
Alright, if you haven't paused it already, try and pause this video and try the next 2 examples on your own. But otherwise, we are going to get rolling. So, checking if this is a perfect square trinomial. The first guy, perfect squared, because the square root of that is 4x. My last guy is, perfect squared. Square root of that is 3. And is the middle term also what it needs to be for this to be a perfect square trinomial? Well, let's find out. That middle term would need to be 2 times, I'm going to put an x for the times there, 2 times the product of 4x and 3. So 4x times 3, so it's 2 times 12x, which is in fact 24x. So this does check out in terms of being a perfect square trinomial. So to factor that, I know my binomial is going to be squared at the end, so I put that squared outside the brackets. And what goes inside the brackets? Well, it's going to include that 4x, it's going to include the 3, and what sign am I choosing? I'm choosing that sign of my b value there, so I have a negative. Alright, last but not least, right, Mr. Athide alluded to before that if you do not recognize this as a perfect square trinomial, you can for sure use logical reasoning. You can for sure use decomposition to factor this. But that's going to be a real pain in the patuchus. And the reason why is, well, okay, take a look at this. Our A and C values, and even our B values, are huge. They're massive. Just full out gnarly numbers. And regardless of what factoring method I choose, my first step is going A times C. And remember, this is all calculator free. So here I am just trying to figure out what's 49 times 25. And well, eventually I get that as 1,225. And now I have to find the factors of that value that add to 70. And I mean, although it's not impossible, it might take you much longer than this sort of question should take you if you do recognize that it is a perfect square trinomial. Eventually, you might find out that it's actually 35 times 35 that give that. But either way, that is not a pretty number to find the factor pairs of that will add to my b term. So it's really important that you're able to recognize this perfect square trinomial, because not only will it save you a lot of effort, it also save you a lot of time, and that precious time can be used for other things, like more math. So, let's check if it is a perfect square trinomial, because otherwise that little tangent was for nothing. Here we go. 49x squared. What's the square root of that? Well, that's 7x, so that's nice. What about that last term? Oh, it is a perfect square. My square root is 5. Does that middle b term cater nicely to a perfect square trinomial? Well, I know that it should be 2 times the product of my a times b, which is the product of 7x times 5. And I do, in fact, get 2 times 7, which is 14x, times 5, which is 70x. And that is, in fact, my b term. So I am very happy about it. You can't see my expression, but seriously, take my word for it. I am happy about it. I know that because it is, in fact, a perfect square trinomial, it's going to factor into 2 identical binomials. So I just write them as that one binomial squared. What goes in that binomial? Well, I have that 7x, I have that 5, and I have the sign of my b term, which happens to be a plus sign. Capiche? All right.
We've got a couple trinomials that might sometimes be mistaken for perfect square trinomials, and we're just going to take a quick look at why they aren't. I invite you to take a moment to look at this first one, x squared plus 4x minus 4. It looks like it has the features of a perfect square trinomial, but why is it not? Mull it over for a bit, pause this video, because I'm jumping in after I select the color purple. It looks like we've got good things going on. X squared is the square of x, and there's a 4 over here. As far as I'm aware, 4 is a perfect square. But you may have noticed that in all of our perfect square trinomials, whenever we squared a binomial, the last term was always positive. Because we are always taking something and multiplying it by itself. There's no way that you can multiply by a real number by itself and get this negative out of it. So this one is not a perfect square, because the last term or the constant term is negative. And that never happens with a perfect square.
All right. What about the next one here? This one looks a little bit more promising. Okay. We see that we have that x squared plus 8x plus 64. I was going to say 24. Whoa. 64. Take a look at that and try and decipher, is this in fact a perfect square trinomial? Do it. Pause it. Did you do it?
I did.
Oh, nice. Okay. Sweet. You've paused. You've come back. Now we're here. So, I'm looking at this. My first term is highlighted, and it is in fact a perfect square, right? X times x will give me x squared. My last term, ooh, that's nice and positive, and the square root of positive 64 is 8. Nice, nice. Now, my b term should be 2 times the product of my a and my b here. So x times 8. So 2 times x times 8 should in fact be 16x. And we know that that could be a positive 16x or a negative 16x because the sign here doesn't matter. It's only the sign in front of my first and last terms that matter. But wait! Hold up.
Hey.
This guy is not 16x. And it's not negative 16x either.
Oh, come on.
Yeah. So, because my b term is not 2 times the product, my first and my last, the square root of the first and my last, it is not going to be that perfect square trinomial. So, let's write that out in words. Since, my b term is not the product of, what do I want to say that? Product of the square root of my first term and the square root of my last term times 2, it is not a perfect square trinomial. Okay, so let's keep in mind it's not the, since my b term is not the product of the square root of my first term, right? So that's the x in this case. And the square root of my last term, which is the 8 in this case, times by 2, but it's not a perfect square trinomial. Woof! So those perfect square trinomials, once you spot them, they're easy to factor, but please make sure you're looking carefully, because sometimes they can look like perfect squares, but aren't. They're imposters. Alright, so there's some practice there in the textbook if you want to give it a go.
Nice.
But otherwise, that's it, that's all. Peace out, homies.
Goodbye.